Okay, it's me again, Jean-Louis Van Bella. I'm a hobbyist in physics. I have a few degrees, serious degrees in economics, and I have a bachelor in philosophy as well. I've got two playlists basically. I'm an ICT professional, and my videos on technology management and artificial intelligence are doing much better than my videos on quantum physics, I would say. But yeah, I want to promote them because first, I do feel that without promotion, without paying for ads and all that, they are doing quite well. And yeah, I put a lot of effort in this. I'm 55, and this journey into this field started very early as a kid when I was reading, John Gribbins, Schrödinger's cat, all these popular science books. And then, I started to read more serious stuff, more serious popular science, if that's not a contradiction in the terms. Roger Penrose. And this video actually is born a bit out of frustration because I'm actually no longer ashamed to talk about this hobby of mine because I do think there's value in it. I think that value is shown from I publish on ResearchGate and academia.edu, and I get thousands and thousands of reads. But this one was a bit born when an acquaintance of mine said, "Well, your videos, that was followed by an ad by Brian Greene, his latest book, Until the End of Time." And I googled the on YouTube and this book because I didn't know he came out with something new. Mind, Matter, and Our Search for Meaning in an Evolving Universe. And I thought, like, oh no. Everything what I've been doing in this field is actually to sort of bring it back to basics and come up with some theory that doesn't is not a theory like anything goes. And but yeah, these are still best-selling books, and I wonder, I said I'm 55, 30, 40 years ago. Yeah, Green or similar authors. Green is now 61, I think. Distinguished professor in Columbia University, like Roger Penrose, and they're still producing the same nonsense, I would say. I said the ad was particularly in Brian Greene, sort of talking about time reversal, multiverses, the many world hypothesis, and that's where I want to save you time when you're also looking for truth and meaning in life. Well, you're not going to get much out of these books, I think. My struggle has been really to sort of indeed bring it back to basics. What sort of I wrote a lot of papers, and I fed a few actually to ChatGPT. I said, like, can you make a book out of my 50 papers on ResearchGate? And what I found out is ChatGPT sort of is it's artificial intelligence, and it can parse documents very well, it can parse mathematical formulas, but it didn't have much of a clue of what my interpretation, which I call a realistic interpretation of quantum mechanics, is all about. And the good thing about it was that ChatGPT did sort of provide very constructive criticism. Said, like, perhaps you should structure your stuff better, and it starts with and that was a good advice, I think. Framing clearly, the history of what you're working on, and then I really mean the history, from 100 or 150 years ago. I said my interpretation of quantum mechanics is basically the one that Einstein, the younger Heisenberg, Bohr, Schrödinger. Dirac has always been a mathematician rather than a physicist, so I won't mention him as one of the people who inspired me. Schrödinger very much. He was his wave equation is I'll talk about that, is is the one that triggered a lot of debate. And ultimately, Schrödinger did not agree with the later interpretation of the solutions that came out of his wave equation, where he said really these are equations of motion of what, of a charge, and he refused to sort of say that, well, my wave equation and the solutions that come out of it, they model probabilities only, because that's the main difference, I think, between what I do or believe in, and I'm definitely not the only one. It is sort of a classical reconstruction of quantum theory, and it's a classical one in the sense that I only think there's one force, the electromagnetic force. Because why do I think that? Because the force, said I've got a degree in philosophy, and I love metaphysics, but I especially like analytical philosophy. The British said that, what's your definition of this or that concept, and make that definition precise. Make sure that you know what you're talking about. And so I thought a lot about the concept of a force and concept of a particle, and a force is a fundamental concept, a particle much less so, I think. I will explain that in a minute. A force acts on a charge, and the only experimentally measured charge is the electric charge. You say, well, we have color charges, and we have strong or nuclear charges, and etc. That's what I put here. There's no color charge, red, green, blue, or any mix thereof, and strong and nuclear charges, they don't have a physical dimension. There's no SI unit. So for a charge, we know it's measured in Coulomb. For distance, we have meters, time, seconds, energy, combination of Newton and meter. We have physical action, Newton meter second, the dimension of h bar or h. So if the theory was sound, I think 2019, the revision of SI units, I think that's the major recent event, together with there have been other things. But the revision of SI units, I think the Nobel Prize Committee should award collectively a Nobel Prize in physics to the professors who did that, because everything is in there. It all gets reduced to physical dimensions that we can measure, that we see in experiments. And color charges and strong nuclear charges. What unit would we use? I said for colors, colors. The stronger nuclear charge, we know that Yukawa had a theory of a nuclear potential, and well, I see that. I wrote stuff on that. I have papers on this Yukawa potential and the nuclear force hypothesis in general, and I strongly believe you can reduce it to dipoles, magnetic or electric dipoles. My theory is very simple. Proton is a three-dimensional oscillation of the proton charge, and a neutron is some combination of positive and negative charge, which makes it neutral as a whole, but explains why Coulomb scattering does occur, why a neutron has a charge radius, or a Compton wavelength if you look at NIST. Let me quickly go to that, actually. The funny thing is, if you're a bit like me, you will wonder like the Thomson cross-section and hard scattering, elastic scattering. It's much smaller than the electron radius, so that says that there's probably some hardcore inside an electron. An electron, an atom we know is a lot of emptiness, and then electron whizzing around the nucleus, the proton. But how do we get that formula? There is a very precise formula for it. It is the classical electron radius, also known as the Lorentz radius or the Thomson's radius squared, times p. And then we have this 8 divided by 3 factor, which is linked to, I may get there, to the way you calculate a cross section, because a cross section and a charge radius, a root mean square charge radius of the proton, and this has been measured very precisely now. And the funny thing is, quantum theory doesn't give you any explanation of these radii, because they basically assume that all fundamental constituents of matter are infinitesimally small point-like things, quarks to be precise. In this theory, I don't believe in. You will say, well, there's been Nobel Prizes for that. Well, I'll talk about where things went wrong, according to me, and why a Nobel Prize is not always. It's probably a sign of scientific value, but the interpretation of stuff is not always. So a neutron said has a quantum wavelength, or reduced quantum wavelength in this case, so it does interact with photons, which means there must be an interaction between the photon and the charge or charges inside of a neutron, a positive and a negative one. It's much smaller than the charge radius of a proton. But you know, these terms, you shouldn't confuse them. A quantum wavelength. Well, if you look it up on Wikipedia, you'll get a different definition and this interpretation there. But a charge radius and a cross section, they are very different things. This is an interesting one, the deuteron. Deuteron is the nucleus of deuterium, of the isotope, of an isotope, a rare isotope of hydrogen. It has a very small charge radius, and it consists of a proton and a neutron. And it's much smaller than the proton radius or the neutron radius, as we can derive it from the quantum wavelength. And that's sort of the thing where I always wondered, even when I was young, like, well, I dig into quantum mechanics and, you know, Feynman's lectures and more advanced stuff, and you never get like a decent answer on why is this a radius. What it is, and you will never get an answer in these new theories. Why? Because they talk about probabilities, but they believe that there's let me go back to my book here. Yeah, they sort of I think that's the main modern mainstream interpretation of quantum mechanics, is that, you know, we have probabilities, and they are not rooted in some kind of physical process. We just have to work with these probabilities, and that's sort of where I think religion or guru physicism or smoking gun physics, or whatever you want to call it, is that's what Lorentz complained about, Hendrik Anton Lorentz, in the his last. I'm going to talk a little bit about that. That, you know, at some point in time, scientists replaced the notion of determinism, statistical determinism. Velocities may be very high, and, you know, we cannot know exactly the position, or can't measure it, or we disturb the position, but they replaced it by you know, purely probabilistic interpretation of what might or might not be going on. So that's sort of what I think the mainstream or Copenhagen interpretation of quantum mechanics. If you look for a good definition, you won't find it, but the one my definition is it, you know, it's a framework to work with probabilities, and with probabilities only. There's no real effort anymore to look for the physical processes behind. And that's sort of where I'm going. Like, you know, that's not about physics anymore. That's not scientific. So I think mainstream, belongs to a group of theories which suggest that, well, any theory that suggests that probabilities are just probabilities, and that we can't have any idea of the physical processes that lead to these probabilities, in terms of, you know, surface areas or you know, interaction theories. That's ultimately rooted in religious or metaphysical concepts, beliefs. Yeah, that sounds kind of vague, but the thing is, if you think there's only probabilities, it comes with you know, these many worlds interpretation, and it also comes with like ideas that you know, the Feynman diagram, an electron is a positron going back in time, or the other way around. You know, we can reverse time. It comes with a lot of crazy stuff. Let me talk a bit about time and why time reversal would not be possible. You know, if we have like a velocity v, you know, we measure that by saying, you know, a particle, and that's the idea of a particle. It should be somewhere. at any point in time. And I'm gonna talk about these graphs in a moment. Yeah, you can say, well, let's put the same velocity we can measure by a minus sign, and here also minus, so that's plus plus, right? But the minus minus. What think about what a negative distance interval would be? What physically what would that mean? You would say, yeah, negative distance interval. Yeah, that makes physically sense. That's just, we measure in the opposite direction of the plus x direction. So that's a particle going in the other direction. Well, then you know that if you're talking about that thing, yeah, then we're going to basically be retracing where that particle came from in the past. That does not mean that the particle can travel back in time. No, what we're doing here, putting a minus sign, and that's sort of where I think sometimes the mathematical symbolism, a minus sign in front of a scalar variable or a minus sign in front of a vector. Yeah, we can have a negative velocity, of course. We can have, particle that travels in this direction instead of that direction. That's a different particle, right? And so that will have a negative velocity, although we know velocity itself is inherently not negative. The minus sign relates to the the spatial reference frame, 3 dimensions, and the nature of an axis in space is not like the nature of time. Time goes one way only, and you can have a lot of theories about why that would be so. My theory is very simple. Kant, Immanuel Kant, a great philosopher, said once that space and time are categories of the mind. They are not part of the real world. I'm not like Kant or other philosophers who say, well, there's like reality and there's our perception of it. No, we are in reality. Once you put an object in, once we observe an object, the reference frames gets established by us looking at that object, and then if it will usually move. If it doesn't move, the position of that object vis-a-vis the observer, us, establishes the spatial reference frame. And then when it starts to move, it moves in one direction in time only. Time is of a totally different nature, and so there's no dichotomy between space, time. They're real at the same time. Yeah, they're a bit categories of the mind in the sense that we will measure time in terms of the velocity of that object, and once you allow particles to travel back in time, you would get something like this. Look at this graph. So we have position x. The thing has a certain velocity. It decelerates. It accelerates again, and then here it goes back in time, and here it goes back in time as well. And then it moves forward in time again, and then it goes back in time again here. This is not a well-behaved function, and it's contrary to the idea that we have of a particle. A particle cannot be at 3 different points in space at the same time. That's just a logical inconsistency. And in reality or whatever in our mind, I don't care. This is a well-behaved function. The particle accelerates, slows down, goes back. Sorry, I should have put that here, the same position in time. It goes back to the position where it was a while ago, and then it moves away again and goes back to the same position. So this is a weird function, but it's one that is possible. The forces that work on this particle and make it move the way it's depicted here are kind of weird, but it's possible. And so that's the fundamental thing where I believe that you shouldn't make things too complicated, and time reversal is impossible because time is time and space is space, and motion is motion. And the most fundamental concept is motion. We know, I mean, that's way before the 2019 revision of SI units, that the speed of light was established as a constant, was defined as a certain value. So energy, the same thing. Energy itself is not negative. When we measure negative energy, it's because our zero reference point. Our reference point for zero energy is some free electron at theoretically very infinite distance away from us, and we bring that electron closer to another electron. So we work against the force, or we work with the force, attractive force, repulsion between like charges, or so the energy, the negative sign is not something that implies there is negative energy. No, it's just direction from some 0 point, a reference 0 point that we choose. So if we talk about a particle also, it cannot be in some kind of zero energy state. That's Dirac was intrigued by that. He looked at electrons, positive energy states or negative ones, and positrons, should theoretically exist. But the superimposition of a positive and a negative energy, so it should be zero energy state. Well, zero energy and zero spin particles are not the same. Zero energy particles don't exist. So where did the madness? When and where did the madness start? And that's something I want to show now. If you read one paper of mine. It should probably be. Oh, I don't pull it up here. Yeah, this one, the Breu's matter wave concept and issue. So now in 29, the Breu got his Nobel Prize for his hypothesis, and so I wrote it here from his thesis in 1924 and 1921. We may conceive that because of some grand law in nature, we can associate a periodic phenomenon of frequency nu zero with each energy packet. So he talks about a particle with rest mass m0, non-zero rest mass, such that Planck's constant times that frequency is the equivalent energy of that particle with rest mass m0, and the equivalent energy is m0 c square, of course, the Planck-Einstein relation. Sorry, the mass energy equivalence relationship of Einstein. So this frequency nu zero is, of course, to be measured in the rest frame of the energy packet, and that's the basis of a theory, and it's worth only as much as the consequences that can be deduced from it. So it was a great theory. The problem was that this wavelength, we can have two kinds of wavelengths or oscillations: orbital or elliptical, or circular things that go round and round and round, and then sort of like photons are linear oscillations. They have a wavelength. A wavelength divided by 2 pi will be the radius of some circle. And so he talks of a periodic phenomenon, and this is the thing where the first pages of the Breu's thesis read really well, but then comes the thing that here I jump to Dirac, and let me do that. Okay. Dirac and Schrödinger got a Nobel Prize a few years later for his own wave equation, Dirac's or Schrödinger's, and they give rise to some, it's actually Schrödinger's wave equation, give rise to some rather unexpected phenomena concerning the motion of the electron. And so the electron is, that's what I want to say here. My theory is that an electron is basically a planar oscillation, a little charge going around and round and round, and that charge has the classical electron radius, and the radius of the electron as a whole is the Compton wavelength. But it's sort of, he found that the trivial solution to Schrödinger's equation is, the elementary wave function, and that shows that, every electron in an atomic or molecular orbital, which moves very slowly, and the classical velocity, as Bohr worked it out, is quite slow. It's really a fraction of light speed. Must have a very high frequency oscillatory motion of very small amplitude, and the amplitude is a radius, superposed on the regular motion which appears to us. As a result of this oscillatory motion, the velocity of the electron at any time equals the velocity of light. And then he says, well, I cannot predict that. We cannot verify it by experiment. But that's sort of where it's great. And here I worked that out. If sort of an electron, you indeed think of small charge that whizzes around at speed of light c. We know that's going to be equal to the radius of that oscillatory orbital motion times the orbital frequency. And then we combine with the Planck-Einstein relationship and Einstein's mass-energy equivalence relationship. You find the Compton radius. Compton radius is something we'll find about Compton wavelength, but it's Compton radius divided by 2p. It's h bar divided by mc. And that gives a very precise, for me, explanation of the classical. I quote here Dr. Patrick Leclerc. I think he's, I looked at a few courses in physics, and his interpretation of the Compton wavelength is sort of the scale above which the particle can be localized in a particle-like sense. And so yeah, visualize that. Things go round and round and round. And now the mistake is that if you look at the Nobel Prize Committee here, I think they, of course, the Nobel Prize was awarded jointly to Erwin Schrödinger and Paul Maurice Dirac for discovery of new productive forms of atomic theory. Yeah, for sure. And then you look at the presentation speech made by this Dr. Pleyel, the chairman of the Nobel Prize Committee in '93. And then it becomes really, like I said, this interpretation of de Broglie's matter wave, the frequency. He draws the wrong conclusions. The result of this theory, when one is forced to the conclusion to conceive of matter as not being durable, or that it can, cannot have a definite extension in space. The waves, which form waves in plural, which form the matter, travel in fact with different velocities. So different phase velocities, and there's a group velocity, as you know, and must therefore sooner or later separate. Yeah, we have this dispersion relationship. Matter changes form and extend in space. The picture which has been created of matter being composed of unchangeable particles must be modified. And that's where I'm going, that's a religious talk, because, well, frankly, particles don't dissipate. And so, yeah, if you think of a particle as a wave packet rather than a single oscillatory thing of waves composed of waves of slightly different frequencies, linear frequencies, then then you will have a group velocity, phase velocity, and because of dispersion relation, and you get a lot of inconsistencies. And I pointed out these inconsistencies. If you just, I think that's the original sin of modern quantum mechanics is, de Broglie's wave packet is non-localized. It disperses indeed, and then you need to find a lot of hocus pocus theories and arguments to make sure that your theory makes sense, and it's not necessary. And sort of that's where I talk about wave equations here, Dirac's and Schrödinger's, which I think Schrödinger's wave equation is relativistically correct, and there's a lot of interpretational problems, and so it gets perpetuated and perpetuated ever. The other paper I want to show is this history of quantum mechanical ideas. I was in touch, like, I think 10 years ago, with a young scientist, Dr. Kansa, and he traces all of the nonsense, as I write here, in modern physics back to conferences organized in the US. Or by US scientists after, the dreadful thing, the atomic bomb and whatever. And he's, what I feel is a bit that, it's sort of, well, atomic theory, there's some secrecy around it. Yeah, I think there's an element in that. The other element is probably that, for modern, for huge investments, public money being invested in huge research facilities, you cannot admit that it's the end of physics. We know everything. So yeah, some mysterious stuff gets injected there. But I think the history goes back way earlier. I talk here about the Solvay conferences, not of 1948. After that, it sort of but Rutherford in 1921. Lama's contribution, there were these were classical quantum mechanical electron models that basically were it for me, and especially in 1928, that's sort of probably where things really went wrong. It says 1928 and then 29, de Broglie got his Nobel Prize. But with a wrong, I think, interpretation of the wavelength or frequency he found, orbital rather than linear. And Lorentz, he died in 1928 after the conference. So the papers have, an announcement of his demise with a big black lettering, regretting his death, as it was a wound infection or something. But he said, yeah, it's this Bohr and Heisenberg interpretation, in terms of pure probabilities that cannot be further explained. He says it, there's difficulties in these theories, and I translated because it's only in French. I haven't seen, so I translated this myself. he said, you know, we need to form ourselves an image in the mind, and such image cannot be non-deterministic. I said I would still like to keep my deterministic belief in fundamental phenomena. Perhaps a deeper mind could know the movements of the, you know, we should keep determinism as an object of faith, to do scientific work. Why do we have to elevate indeterminism to a philosophical principle? I think he says it all there. And so yeah, there's another thing I want to show you here, another paper, which is a simple one: the difference between a theory, a calculation, and an explanation. I feel, you know, mainstream quantum physics suffers from you know, anything goes, any theory is right. Well, no, a theory that doesn't respect the conservation of energy, that has non-conservative forces, conservation of linear and angular momentum, conservation of charge. I don't think that's a good theory, because it does away with these very fundamental laws that underpin all of physics, and deterministic worldview, statistically or real. So you can have calculations, and as we know in modern mainstream quantum mechanics, there's a lot of calculations that are really on the limit, or over the limit of making mathematically sense, infinities that go away when you normalize, or you know, apply theory that does depend on a gauge, unlike electromagnetism, which is gauge invariant, and an explanation. I think the classical mechanics offer an explanation, and so that's where I want to maybe. I'm gonna pause and then continue to talk. I discovered the pause button on my screen recorder, but that's sort of where and again the you know, books really that mind, matter, or search for meaning in the universe. You know, that's religious humbug. That's not science. That is not um, you know, our mind, our faculty of thinking, really analytical thinking. You know how difficult it is to focus on something. So what is it? Well, it emerges from very complex biochemical processes. We are a biochemical machine, I would say, or mechanism, or organism, which ultimately is electromagnetic in nature. Our nerves, you know, our body's chemical processes. It's all about, you know, charge currents and electromagnetic fields, and all that kind of stuff. That's and so our mind does emerge to deal, from survival, you know, fighting bears and animals a long time ago, and now we apply it to the reality around us. And the amazing thing is that we understand, we do know it. I do feel that all that is left is you know, really engineering and practical applications. So my son and daughter, that's why I encourage them to do study engineering. You know, physical principles, they are known, they're fixed. There's nothing left to discover. And all these modern quark, gluon, whatever, these models, they're useless. That's something else I want to show you very quickly before I take a break. Is the other thing I was interested in is here, Realist scattering. You know, as a kid, I was interested in, why is the sky blue? Huh? Why does it appear as blue? And why are clouds the color they are? You know, white on a sunny day, and yeah, very dark gray, almost black when they're about to when a thunderstorm arrives, and you need to get away, or avoid it on your bicycle, because you know you're going to be wet very soon. So the reflection, why certain colors, photons with a specific wavelength get reflected and others get absorbed, or why they get scattered more than other frequencies. Blue light it has more energy, the photons, than the red light, and so they get scattered more. And the funny thing is, what I realized is that well, you look at content scattering, you know, these theoretical articles, and you know, the angles, and but it doesn't explain these kind of things. And you know, most of the stuff that is interesting in physics and the questions you have about, you know, reality, or as Feynman writes so beautifully, you know, the crystals in wine and whatever, you can't explain it by elementary physics. You need electromagnetic theory applied to very complex structures, molecular structures. And so I warmly recommendedly reading about Rayleigh scattering and all that stuff, and content scattering. I will talk about that probably after my break, and then say like how limited it is in terms of explaining real life phenomena, because it's based on a model that is far from complete and too simple. So that's it. I will take a short break. I'm at 34 minutes in the presentation, and yeah, I'll resume this podcast, or whatever you want to call it, audiobook, in a moment. Okay, I'm back. I want to show you, maybe if you want to have an easy introduction. I did write a manuscript, and I initially had an interest from WSP, Morgan Claypool, the publisher behind the Institute of Physics of the United States. But they, in the end, it got reviewed by scientists, physicists that probably didn't find much of their own theories in it, even though they were also Zitterbewegung theorists, because my interpretation of physics isn't very different from what I already said about Schrödinger's Platzwechsel models. So you have these graphs here. The thing I want to show is relativity theory, if I have it somewhere, because that's a nice introduction to here, yeah. Special relativity theory is kind of more intuitive than you think. Imagine that velocities could be infinite. There must be an absolute speed limit on everything. On charges, on photons, on spaceships, bicycles. So this is sort of a joking story I tell here. You have this Lorentz formula, the mass times the Lorentz factor, and you see this curve, and then you wonder. This is what I'm going to show now. Can we push this to things? Can we apply this to things which have zero rest mass? And there you come and said you have usually this curve and it goes to it hits the absolute speed limit, and the formula, the inverse a Lorentz factor is just an arc of a circle. It sort of looks like a difficult formula, but it's quite a logical one. Now, if you have something with zero rest mass, what would it be? Well, photons in the first place. Photons, as you know, they always travel at the speed of light, and they can have any equivalent mass, I would say. Mass is energy when we're talking. But you can have things with zero rest mass, photons. And then we have two things, I said my Zitterbewegung hypothesis is that there's like two kinds of charges. We have electrons and protons. These are the two fundamental stable particles, and I said both are an oscillation of charge orbital. And the what I call the effective mass, an electron, I'm not going to go too much, but you have it here, a charge whizzing around and around and around, and we have a sine and a cosine, cosine plus E as a rotation factor with a phase, the phase of that is E. So this would be the mathematical representation of an electron. And what's special about it is that we can analyze it in terms of classical mechanics of velocities, linear momentum divided by the mass factor. Velocity is the radius of that oscillation times the orbital frequency. And what's here is I say C is equal to A times that frequency, and then I have my electron model. E is mc squared. It's a very easy physical interpretation at the microscale, I would say, of Einstein's mass energy equivalence, the Planck-Einstein relation, h bar times, and I get my content radius, and that's really it. And in the electron, of course, say what keeps it in place. Well, this is a ring current, and it generates an electromagnetic field, a magnetic field. It's like a tiny magnet caused by the ring current, and so half of the mass of the electron is in the electromagnetic field, is the equivalent mass of the energy in that field, and the other half is the effective mass or the relativistic mass of that point-like but not infinitesimally small charge inside of the electron, which is much larger. The Thomson radius the hard scattering radius of an electron is a fraction of the total Compton radius of an electron. Is that 1/2, which you see in Schrödinger's equation, and that's also where I think, you know, interpretations of Feynman of Schrödinger's could say, oh, it's not relativistic because that 1/2 factor is the factor that you have in the classical non-relativistic formula for kinetic energy, 1 divided by 2 times mv squared. Well, no, it comes out of that model, and for the proton model, things are more complicated because the Compton radius is not h bar divided by mc, it's 4 times it. 0.84 times 10 to the power minus 15. And you have a much more complicated thing. You need to use a vector equation, because I think of a proton as a oscillation in 3 dimensions. And this is something I haven't worked out. I mean, the equations of motion. Let me show you. I actually got inspired by engineering, and you know, Ducati engine versus a Harley Davidson, the banking angle between 2 cylinders. If you have 2 linear oscillators in a right angle to each other, but you can extend that to a star engine, you can think of this linear motion that gets converted into circular motion, and potential energy that gets converted into kinetic energy of the pistons, and that's where the model comes from. This is the model. 2 linear oscillations make something go round and round and round, and there's no magic to it. It's just you know, the naked charge inside of an electron generates an electromagnetic field, and that keeps it in balance. And it obeys the Planck-Einstein relationship. That's when a photon, when it hits the electron, is going to mess with the electromagnetic field. It sort of gets absorbed, and then we have a disequilibrium situation. And so at the end, you know, a photon will be ejected with the same frequency or another frequency, hard scattering, elastic scattering, or inelastic scattering. And so that's the model, really. Clean up my sheet, my notebook. Yeah, you will say, what are the equations of motion then? Here I took, I should acknowledge it, MIT OpenCourseware, a course for kinematics. It becomes complicated. I said we can imagine easily a you know, an oscillation in a plane, but you know, an oscillation simultaneously that goes up and down, sideways and back and forward. That's kind of difficult. And how does the energy partition theorem work with it? I haven't worked out the equations of motion. That's sort of something maybe I want to show as well. Is in my papers. I have one that does really badly, but which I find interesting. I call it one of my mystery, but these are true mystery papers. Fine structure, mystery 105. As you can see, I have my ICT things. Here, the proton yarn ball puzzle, I call it. What is actually the trajectory of a of the elementary naked charge inside of, and that's where it becomes very difficult. Is it a toroidal or a spherical proton? There's many possibilities, and I haven't made sense of that. I will be honest about it. So I'm lacking the equations of motion, I would say, for the naked charge inside of a proton. But I think my model does make sense, and that's it. So to go back to the problem of scattering. Let me open my notebook again, with a different tome. Yeah. That's sort of where you know, this is my electron, right? It's sort of it has a size, goes round and round. So that's the you know, the thing that goes round, but we look at it sideways. Okay, so it's a ring current. It generates this magnetic field, and that's what keeps the electron spinning. Let me clean up my sheet. So basically, what happens now when a photon comes in? It may hit by accident the naked charge immediately, and then, you know, it gets scattered in this direction or that direction. The idea is that we talk about a free electron, is that the electromagnetic field of the photon will mess with the electromagnetic field, with the charge itself, and because it's a disequilibrium situation, it does want to return to its normal situation. It's going to radiate the energy it gets from the photon straight back out in a certain angle. So that's one way. That's hard scattering, but I'm gonna say immediately why I think that. There's a little thing there. It may also sort of, we know that the magnetic field is incredibly strong. I calculate that in my papers. Inside of that ring current, and so the photon energy is much less than the electromagnetic field, but it's also going to cause a disturbance of the electromagnetic field that keeps our charge spinning. And so yeah, we're going to have a photon that gets emitted with a different frequency, the same frequency, a different frequency is my theory, and it's gonna, the difference in energy we know is gonna change the kinetic energy. It's gonna make our electron move, bounce away, and it's gonna pick up some kinetic energy as a whole. And my theory was so far, but I need to admit, is that outside the magnetic field is, it goes down as the distance from the center of our ring current to the power of 5. That's of course a macro. You can see very near the ring current, the electromagnetic field. The magnetic field will also be very strong. So yeah, I think photons mess also. But that's something here in the simple model, hard elastic scattering. You don't get an explanation for why blue light gets scattered more than red light. So that's where I'm a bit disappointed in sort of, even my model. I think it's a good model. But yeah, and I said in reality, Rayleigh scattering and the cross-section is different and depends on, formula that involves the fourth power of the frequency. So it does depend on your cross-section is going to change. So the intensity, because I talk about that in other papers, how do you measure a cross-section? I'm not going to go into that. I'm going to upload that to ResearchGate. You can look it up. Per annihilation and creation, perhaps. What happens when an electron and a positron come together? I think their magnetic fields, magnetic moments need to be aligned or line up. So we have a north and a south pole, or south and north pole. Let's check it. And that's going to line up with the north-south pole. So the condition is positron is not an electron that travels back in time, but has a different spin direction. If this is plus 1h, then it's going to be minus 1h. But the magnetic moments are both up, and then they come together, and it's sort of like two magnets clicking, together. And as we know, there will be two high-energy photons, that's said, resulting from that. I think this is the Dirac process, as it's called, and the reverse process would be two high energy photons that come together and create an opposite pair of opposite charge. In my papers, I think these high energy photons may not be gamma rays, but what does make sense, these heavy bosons that are very unstable and in the end degenerate back into an electron or a positron. And yeah, that's sort of what I say here is it gamma rays or WZ bosons that are involved in bar annihilation and creation. I think the charge conservation law holds not only globally but also very, 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 very locally, like here. And but that the jury is still out on that, and that's then the difference between high and low energy physics, I guess. What else can I show you? Oh yeah, maybe that formula for the Thomson cross section, but I'm not going to go into that. Scattering. It's very complicated to calculate a cross section, and there's a lot of mathematics involved. I said I'm going to upload this a little bit. It talks about solid angles. What is a differential cross section? How do we get the total cross section from it? Nothing is very obvious, and but I would say don't go through the trouble of digging into that too much. It's just to say, like what I showed you here, when you get an A divided by what is it here? Here, this formula is very precise, and you will say, well, it should be the classical electron radius squared. By the way, there's a mistake in that. It says find structure constant to the power 4 times the Thomson radius squared. So that should be alpha square. I don't know where the mistake comes from on this very important website with constants units. But yeah, so don't worry about that factor A divided by 3. It's there because of the model that you have when you calculate a cross-section, which is, as I said, not an easy thing. But that's something I want to also tell you as you sort of want to develop your own models and whatever. Don't get discouraged by a factor 2 or pi. That's what Feynman in the end said. If your formula is off by that factor, then you're probably okay. I do recommend you to dig into theory to sort of distinguish between, differentials of variables and see what the dependent and the independent variables are, and then subtle differences like a solid angle and an angular size or an angular diameter, which you need in this theory. But the formulas do make sense. It's just they depend on so many other things, and yeah, I think I'm gonna take a break again and then see if I missed anything that I should talk about. Probably, but I'm gonna do that in a moment. My theory of what explains a deuteron, charge radius, and other things. I'm at 51 minutes. I think the third session of this lecture or audiobook or whatever you want to call it is not gonna last super long. In the meanwhile, you can enjoy watching this slide here, which has a lot of stuff and a formula for a cross section. Okay, I'm back from my break. I smoked a cigarette. I'm gonna actually wrap up, I think, just by doing what I intended to do, and that's a bit to sort of provide an alternative to paying $20, which is not a lot, for books that will keep the mystery alive. Time reversal, multiverses, does God exist? Does our mind have a trace somewhere? Are we destined to be what we are? Does God exist? And blah blah blah. To my papers. So this one, the whole list of this is an interesting one. The electromagnetic deuteron model. I said it has a few hundred reads only. So now I hope it picks up a little bit. But this is one how you can build up, the non-symmetric potentials and build up what I call spin zero model of deuteron nucleus. Maybe it has been. But it's spin zero model in the sense that we have a proton and it's attracted by a neutron. And why is it attracted by a neutron? Because we think of it as a a proton-electron combination, but in terms of its size, it's it's a special combination. I talk about the Diaz model, which inspired me here in 2008, and I want to give him credit for that. Diaz is a bit like me. He's much cleverer than me. He's really a polymath who writes about everything, medical science, neuro, artificial intelligence, and quantum mechanics a bit. And so he has a few papers on quantum mechanics like me as well. And he models the nucleus using electric dipole potential. I think what's lacking a bit in his model is the dynamics. But it shows that, Yukawa's famous nuclear potential and force is probably just a dipole field. And the advantage of using electromagnetic theory to explain a radius of a force or a force range that is much shorter than what you have in Coulomb attraction and whatever. It also goes into what I call here, if you posit a new force, if you think, this is a new force and we have a nuclear potential and all these kind of things, you need to have a nuclear charge and a nuclear permittivity factor as opposed to the electric and magnetic constant. And that's sort of where in this paper I show you come into logical equations that don't make sense when you do a dimensional analysis on it. Other papers that might be worth looking at are, we had that one already. Yeah, different sort of where I expand a bit more on pair annihilation and creation, which I doubt is really happening. I think there's some fuzzy logic and also some poor accounting. The magnetic anomaly talks about the size of these elementary charges. Mystery papers. Intermediate vector bosons, I think I said W plus minus bosons. There aren't really bosons in. They're photon-like, but they aren't photons. They carry charge. Yeah, my worldview, the uncertainty principle. What is it really? It's not some metaphysical thing. Free will is our mind. It's born in our mind. We can analyze the situation, decide to do this or that thing. But the other thing, whatever we decide to do, is not happening in another multiverse. There's no, we don't multiply ourselves continuously at every branch, at every decision, at every event. Wave function math dimensional analysis, nice mathematical paper. I talk about the end of physics and language of physics. I have a bit of a paper on cosmology. Very interesting that we see that our universe seems to be expanding faster and faster, which may suggest that there are effectively other universes, not multiverses or many worlds, but that there was not one Big Bang, but quite a lot of them, and that maybe other universes are tearing ours apart. But that doesn't mean, that's not a crazy theory. That's a possibility. A mass without mass model of protons and neutrons that explains why I believe. You have this discussion on neutrinos. Neutrinos come out of nuclear reactions. I think just like protons and neutrons are like three-dimensional oscillations of charge. A neutrino is not photon-like. Well, it's a light particle. It's light-like, but it may be a three-dimensional oscillation of an electromagnetic field. And because there's an oscillation in direction of its motion, that's why it might not quite attain the speed of light. That's something I explain in it. Nuclear force, the neutron hypothesis, electromagnetic, we've had that. Yeah, it's sort of the quantization of nature. I have a series of lectures on physics, a bit joking on a joking reference to Feynman's lectures, where I thought like maybe I should rewrite a few of these to push the logic to its logical conclusion. So that talks about near and far fields and how these are modeled. Electron propagation in a lattice. I combine that with Schrödinger's survivor's guide. That's sort of when you get really desperate. Feynman's time machine. Again, the arrow of time. Probability, quantum behavior. Matter waves, amplitudes, and signals. An interesting paper, more of an engineering sort of how does a signal propagate and why it doesn't propagate any faster than a current in a crystal lattice. And that's a bit of, this is very the wavy function as an energy propagation mechanism. Again, I talk about Schrödinger's equation in free space there and point out the similarities with Maxwell's equation. And they are very similar. Schrödinger's equation does model equations of motion. Probabilities can be derived from it based on the fact that when a particle is more regularly appears more often in some place than in another, then the probability to find it there will be higher than at that other place. And that is really it. And I'm at 1 hour, and this may be my last lecture. I really want to get back into biking and sports, and then I will see how this picks up. Hopefully, I didn't make too much bad publicity for Brian Greene and others, so I don't get into trouble with copyright. that has happened before, that a video was taken offline um, by a guy, because I basically quoted from Feynman's lectures, and I showed them on my screen, and they did not like that. Which all is good, because otherwise I'll just edit that part out and republish. Because I invested a lot in this kind of research, and so I think it's worthwhile sharing it with you. Have a nice evening from Brussels, and maybe till